In this session, we have two distinguished guests with us. We have Dr. Utpal Sarkar, an associate professor from the Department of Physics, Assam University, Silchar, and followed by his talk, we have Professor Pankaj Agarwal from TGG Crest, Kolkata. Today's session will start with Dr. Sarkar's speech. Now I will move on to his introduction. Dr. Utpal Sarkar is our very own professor from the Department of Physics, Assam University, Silchar. He has more than 130 publications, 20 book chapters. He has 7,800 citations, an H index of 40, item index of 93. He completed his PhD in chemical physics from Indian Institute of Technology, Kharagpur, and then he has done postdoctorate from Regensburg University, Germany, McMaster University, Canada, CEA Grenoble, France, and another University of Science, Technology, Lille, France. He has been selected in September 2024 as the world's top 2% most influential scientist by the Stanford University, USA, and Elsevier in Netherlands. He is the associate editor of Journal of Frontiers in Chemistry. He works as a guest editor for the special issue in Theoretical Chemistry Accounts. He has received Academic Excellence Award in Assam University Silchar in 2022. He is life member of in the ICS, MRSI, CRSI, and also a member of NASI. He's a guest editor of Journal of Molecular Modeling, and also he is a reviewer in many reputed journals. Today, it's a pleasure of us that he has given his valuable time to share with us. Now I will handle the session to Dr. Sarkar. Sir, if you can start.
Thank you, Varsha, for your kind words for me. Uh, Now I am sharing my PPT. Can you please help me to check whether it's working fine or not?
Yes, sir.
So, are you able to see it?
Yes, sir.
Okay. So, during my talk, I want to switch off the video because of the bandwidth. I am speaking mainly from my home, so there might be some internet issue. If it is, then please bear with us. We'll come soon if any problem comes. Is it in full screen,
Yes,
Borsha?
sir. Yes, sir. Only the presentation is showing.
Yes, only the presentation slides. Fine. A very good afternoon to all of you, especially the participants from various parts of our country, starting from Kashmir to Kanyakumari and from Gujarat to Nagaland. Okay, so it's a very diverse set of participants. I welcome all of you to the Assam University, and Assam University is located at Silchar. It's the down part of Assam. It's a very nice place, and we are on the hilltop. So a beautiful scenery, scenic beauty. You will see if you visit during monsoon season, especially in the morning and especially during sunset. Anyway, this is a small introduction of Assam University. Now we are
कैसा business है कैसा
now We are going to the main topic. Today we will discuss about the quantum chemistry for predicting properties of atomic and molecular systems. So before going to the original discussions, initially we will review the atomic models and concepts. So I will start with Kanad. Kanada was an ancient Indian natural scientist and philosopher who lived between 6th to 2nd century BC and founded School of Indian Philosophy. The name of the school is Vaisasika, and he developed the foundation of atomic stick approach to physics and the philosophy in Sanskrit text Vaisheshika Sutra. So his text is also known as Kanada Sutra. Kanada suggested that everything in this world can be subdivided, but this subdivision cannot go for cannot go on forever, and there must be some smallest entities. The smallest entities is basically Poromanu that cannot be divided, that are eternal, and that aggregate in different ways to yield the complex substances. And he used these ideas with the concept of Atma, this soul or self, to develop the non-theistic means of to moksha. He viewed, if this concept is viewed from the prism of physics, then it simply implies a clear role for the observer as independent of the system being studied. And Kanada speaks about the six properties of the matter, namely these six are drobbo, which is basically substance, guna, which is quality, karma, this motion, samaya, time, and vishesa, this particular, and samayavaya is inherence. So after that, it is Democritus, who is a Greek philosopher, lived between 470 to 380 BC, and it is believed that he is the father of modern atomic thought. He proposed that matter would not be divided into smaller pieces forever, and he claimed that matter was made of small hard particles that is called atomos, and the same was also proposed by Kanada called Atman. After that, it is John Dalton in 1808. He gave the theory of atomic theory. In Dalton's theory, we know that he considered that the atoms are teeny and invisible particles, and atoms of one element are of the same nature. Different elements are of different nature, and compounds formed by combining these atoms. This is Dalton's theory, you know. Then in 1897, the electrons are discovered by J.J. Thomson, and he is the first scientist to show that atom was made up of even smaller things. So these atoms are breakable, and it is one of the composition is electron, and he proposed that the existence of some plus particle, and his atomic model was known as the Reisenband model. After that, it is Rutherford in 1911. Rutherford discovered protons and the nucleus. He showed that the atoms have positive particles in the center and are mostly empty space. These positive particles are called protons, and he called the center of the atoms as the nucleus. This is the well-known Rutherford experiment. In this experiment, there are three particular type of scattering occurs. So here the radioactive element is there, and it emits alpha particle, and here is the gold foil, and here is there is a collection of this particle, so screen. So he seen that most of the particles are basically going through the gold foil without changing its direction straight away. That means this gold foil does not able to change the velocity, the motion, the direction of these particles. That means most of this space of these foils are basically empty and is not interacting with this alpha particle. A small fraction is deflected means that this is plus particle. So here in this gold foil there are some region where these positive particles are there and that are very less amount. That is why you are getting less deflections, and only a very small fraction is totally deflected back, that is scattered by the nucleus. Okay, so that is Rutherford experiment. And after that, in 1930, totally new concept come. That is Niels Bohr improved the Rutherford's model. He proposed that electrons moves around the nucleus in specific layers, that is cells. So from continuous to discrete in some specific layers only. Every atom has a specific number of this electron cell. After that, in 1932, Chadwick discovered neutrons, and in 1932, this is 1932 onwards, this modern model of atomic theory comes, and here it is basically thought that the electrons moving around the nucleus in a cloud, not as a particle proposed by Bohr. Just 1 minute, please. And it is impossible to know where an electron is at any given time. This is basically the consequence of Heisenberg uncertainty principle, and that is why this new concept is telling to consider the electrons are basically in a forming a cloud, and that electron cloud we have to characterize basically in chemistry. So this is the timeline of this. So now come to the original topic. This is the atomic theory, and some part of the information we get atoms, and part of it is quantum mechanics through Bohr, and then the Schrodinger. So this, this year is the 100th year of quantum mechanics. So how these quantum mechanics help us to understand the chemical bond. Okay, that means what is the nature of the chemical bond? What are the participating particles? What is the nature of forces to bind all these different types of atoms in a molecules or in a matters? That we are going to discuss. That means this chemical bonding. This is deceptively simple, but yet many aspects remains poorly understood despite intensive investigation, and it is one of the fundamental questions that has attracted the interest of many scientists past and in present also, in particular in understanding the nature and the nature of this chemical bond. Okay, that means how do the electrons and nucleus move in respect to each other? How the what are the subatomic particles these electrons are participating in chemical bonds, and what are the nature of this force? The force is not only the Coulombic force, rather van der Waals and some Pauli, all these quantum mechanical forces are play into this picture. We'll discuss one by one. So the what we understand till now is that the model based on classical physics is unable to explain the phenomena of orbiting the electron around the nucleus, because it is a charged particle, and if it is in that particular motion, then it will radiate energy and it will ultimately fall in the nucleus who sees to the existence of atom. So that is not possible. So what is the solution? The solution lies in quantum mechanics. When applied to atoms, it gives that the electrons are occupying discrete energy levels as proposed by Bohr. And then now, if we consider that up to that much quantum mechanics, then the stage is now set where the challenge of solving the Schrodinger equation, particularly in devising the approaches for searching the original formalism into subatomic particles, individual solutions basically for this, and using approximate method for solving the full Hamiltonian. The full Hamiltonian consists of the kinetic energy part and the potential energy component. These approximate methods, these are all approximate methods. These approximate methods aims to create a simplified model for enabling the computation, but at the same time capable of capturing most of the useful informations. And in 1927, Max Born and Robert Oppenheimer formulated the Born-Oppenheimer approximations. In this approximation, which allows to separate the electronic coordinate and the nuclear coordinate separately, that means you are decoupling these electronic and electronic motion with respect to the nuclear motion, and that assumption is very much gives very good results and as expected, because the heavier the nucleus, this consideration gives you closer to the approximate, means closer to these original results. Okay, so after that, in 19, this is basically 1927, and then after that, 1932, Huckel used approximate theory again. He considered only the pz orbitals of the atoms and used the linear combination of atomic orbitals to calculate the energies of molecular orbitals, and specifically the pi electronic systems like carbon bonds are there. So ethane, benzene sorts of molecules you can explain with the help of Huckel method. And this approach is basically further extended by Hoffman. And here you see that only Huckel method considers it can explain the pi electron, because you are considering only pz orbital in this. But in the extended Huckel method, you can get the information not only for the pi orbitals but also with the sigma orbitals. Okay. So here, though you are getting the sigma orbitals, but ignores the electron-electron repulsions in these extended Huckel calculations. Okay, so here in then it is Hardy's method comes where also the electron-electron repulsion term is totally neglected. Then Fock, Hardy and Fock made some new theory, that is mean field theory, where he considered that the individual electrons are moving on an average field. That means this electron-electron repulsion along with the Coulombic term electron nucleus, that is included in this Hardy-Fock method, and it gives very good results. But you have to solve these Hardy-Fock solutions, and then it is a Rudhan, Hardy-Fock-Rudhan self-consistent field method is basically the modification of the Hardy-Fock theory. By here, you have solved a very large number of electrons in a self-consistent way. Okay, so these what we are talking about is basically in the late 40s. So significant contributions have been done for these characterizing the atomic and molecular system by Hardy-Fock, and Rudar. Okay, now the next is basically what does this quantum chemistry means. Quantum chemistry is a branch of physics and chemistry that makes use of quantum mechanics to study chemical system on an atomic level. Okay, so it is basically interference of of physical phenomena, physics related things along with chemical aspect are there, and you are using quantum mechanics to look into this system in chemical sense, and the flavor you will get, the atomistic level flavor you will get. So how do you now move from Schrodinger to the present day quantum chemistry? Why Schrodinger? Schrodinger equation is exact in nature. You will get for one electron system, you will get a completely solvable equation, and you will get a solution for it. Okay, so no problem of approximation. If you consider hydrogen atom, you will get closed loop, closed form solutions. But in quantum mechanics, there are this is a many body problem, and you have very large number of electrons, very large number of nucleus. Nucleus part you this Born Oppenheimer approximation can take care of. But what about the electrons? There are a large number of electrons. Okay, so you have to consider some sorts of approximation, and these are the approximate method we have discussed earlier just now. Okay, so initially it is basically started by pen and pencil paper in 1927. This is Headler-London theory, where they consider two hydrogen atom at a very large distance, and then it how the bonds are forming if the two hydrogen atom moves closer and closer, and then form a molecule. When forming a molecule, there is a bond between these two. Okay, so this is the nuclear, this is the potential energy, this is basically the total energy of the system. This is the total energy, this is the potential energy, and this is the kinetic energy. Okay, so and this is the x-axis, and this is the distance between the two hydrogen atoms, and this is basically the total energy of the system. So you see that initially when they are very much separated, the the total energy is basically zero. Total energy means only the if I consider the interactions between these. Okay, it is not the hydrogen atom and hydrogen atom minus 13.6 and minus 13.6 is minus 22 27.2 electron volt. That I took as a reference point as zero, and then if I move closer and closer, then the potential energy, this total energy of the system is basically very low here, and here you will get a bond, and then if you just squeeze, then it blows. Okay, so it's unstable. So at this point you will get a bonding, and this is the first work on quantum chemistry, I believe. But this has been done totally on the pen and pencil. Okay, pencil and paper work, no computer use. But we have solved the Schrodinger equations in an approximate way. But after that, PM Dirac told in his Nobel lecture that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. So it's very complicated to solve. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computations. Okay, so ideally, if you use Schrodinger equations and able to solve it, then the whole of the chemistry is basically solved. But when you do it practically, because this is a nonlinear, there are in the potential energy, so many nonlinear terms are there, and it's a many body problem. So you cannot get a closed loop solution for that. Numerically, you have to do, and that is a very tedious job. Then it is the computer, digital computer, which basically help us. The first computer calculations is done by on a diatomic molecule nitrogen in 1955 by Suar. He is basically the student of Mulliken, who is a Nobel laureate. And this molecular orbital theory, is basically developed by Mulliken. Now, this is what we have talked about is basically the wave function based techniques, which is basically very, very time consuming and heavy calculations. What is the alternative of that? The alternative is the density functional theory. Another, I will now talk on this density functional theory. But why we are using this density functional theory? This DFT help to help the analysis and interpretation of the experimental data. Whatever the analysis we will do in the experiment, this theory can able to analyze the results and interpret the results, and it can help to uncover new laws and formulate new theories. It also helps to solve problems and hint solutions before doing the experiments. There are so many examples of it. And it helped to design new experiment also to predict properties and quantities that are difficult or even impossible to observe experimentally. That you can also do. So our first example will start from this. Now, when we are doing this one, what does it mean actually? We are doing some calculations, we have some simulations using computer that are basically computer experiments which help to mimic the reality. The reality means what are basically doing in experiment, that particular environment we are basically mimicking in our computer experiment, and it is based on the assumptions, approximations, and simplification. That means we are basically developing the model for these DFT calculations using these assumptions or simplifications. What are the important characteristics of this model? It is basically very simple and general, very general or specific, that is relate only to specific system or problem, and its limitation, there are some limitations. One must always be aware of the range of the applicability and limits of accuracy of these particular models. There are so many inherent features within this DFT. So the functionals, the basis sets, etc., etc. So you have to cautiously use these functionals and basis sets, and cost efficiency is very, very good with respect to the wave function based method. CPU time is very less, memory is also very less, disk space is also very less. Why? Because in wave function based method, you need for each electron 3 coordinates x, y, z for a particular, and if you consider spin, then 6 coordinate to represent a single electron. And if you have n number of electron, then you need 6 n coordinates. However, if you consider instead of that one only density, then it will be reduced too much. Okay, no need of this wave function. Is basically the electron density that will tell you the rest of the things. So what are the computable quantities? It is molecular structure that is closely tied with the energy. Energy means the potential energy. And the whole of the potential energy surface you can explore, not only the ground state energy, but the whole of the potential energy. So this is extremely useful when doing the reactions. and molecular properties that can be compared or used to interpret the experiments like thermodynamics, kinetics, spectra like UR, IR, UV, NMR, etc. And properties that are not experimentally observables like bond order, like aromaticity, molecular orbitals that you can also quantify here, which helps you to characterize the molecule. So in short, these molecular energies, energies for transition states, bonds, energy, reaction energy, molecular orbital energies like HOMOs, LUMOs, multiple moments like dipole moment, quadrupole moments, atomic charge on each side of the molecule, electrostatic potentials, vibrational frequencies, and NMR properties, reaction pathway, how the reaction goes. These are the things you can do. So what is the basic theorem behind this density functional theory? There are two basic theorems. I just tell one by one. Theorem 1 tells you that there is a one-to-one correspondence between the external potential and the electron density. It means that if you know the electron density of a system, it is possible to characterize the external potential or vice versa. If you know the external potential of the system, you can estimate the electron density of the system. But this first theorem cannot tells you how to get the electron density, because this is the main crucial information I need to know, because density functional theory means everything can be derivable from the electron density of the system. It is the electron density which plays the key role here. But the first theorem is not telling how to do it. It is the second theorem which tells you that if you use variational principle, taking your model for ground state Hamiltonian, then taking a trial density for that, you will get some source of ground state energy, and if it satisfy that particular relation, that means if your electron density, if you take as a true electron density, then you will able to get the ground state energy of the system and ground state electronic structure of the system. If not, then whatever the energy and structure you are getting is basically the higher than that, that means the excited state. Okay, so using variational principle, you can solve this problem. So when doing this one, so this is the ground state energy, and this is the electron density of the system. This is the total number of electrons. So if when we are performing a constant variation is keeping the number of electron constant of the system, then delta of these E minus mu integration rho or dr minus n is equal to 0. This is basically the Lagrange undetermined multiplier, which tells you that this it is basically Professor Robert G. Parr in 1980s. He identified that this Lagrange undetermined multiplier is nothing but the chemical potential of the system, and it is basically mu is equal to del rho of E. So if you take the differentiation of energy with respect to electron density, then you will get the chemical potential of the systems. So once you know the chemical potential of the system, that means the whole of the chemistry is now getting inside this density functional theory, and the popularity of density functional theory is basically blooming after 1980s, because it is rightly pointed out by Professor Parr that this is nothing but the chemical potential of this Lagrange undetermined multiplier is nothing but the chemical potential of the system. Okay, and then this most of the chemist people use this density functional theory to characterize the organic system, especially the molecular structure of the system. And in 1998, Nobel Prize goes to Professor Walter Kohn for his development of the density functional theory, and John Poppel for his development of computational methods in quantum chemistry. So Walter Kohn develops mostly the functional density functionals, and Poppel is mainly developed the basis sets for these Gaussians. Gaussians people are using. So this is the rough potential energy surface of a system, and this is the reactant, and it goes through a transition state, and then finally goes to the global minima. This is the product of the system. So when we are doing this density functional theory calculations, we are basically doing some sorts of response properties. These response properties are with respect to energy, with respect to magnetic field, with respect to nuclear field. So depending upon that, we are getting different sorts of property. One is energy, another one is force, that Hessian, these harmonic frequencies, and then dipole moment, then IR, polarizability. So these are basically different sorts of energy derivative with respect to these response functions. Okay, with respect to this response, so when you are applying a magnetic field, electric field, or by mechanical change means the distance between the atoms, then you will get different of sorts of properties, and that manifests as the property termed as this one. Okay, so this one we have already discussed, and now we will discuss some sorts of chemical reactivity parameters that has been emerged from this chemical reactivity. So there are two sorts of chemical reactivity parameters. One is global parameter, another one is local parameter. Global in the sense that when we are changing these external perturbations, and then whatever the effect we are getting from this particular molecule or atom is basically overall property of the system. However, local property means we are giving the external perturbation to the system, but we are now measuring the change locally. Means suppose we have water molecule, I want to see the effect of the external perturbation on the hydrogen atom, one of the hydrogen atom, or one of the oxygen atom present. That are local properties, and global properties means as a whole molecule. Just wait a minute. I'll take some water and then coming back. So, so this is global parameters. First one is the chemical potential, which we have already identified as derivative of energy with respect to the number of electrons, keeping the external potential fixed. Another one is the electronegativity. Electronegativity is basically the same thing with negative sign. Chemical hardness, which is basically the second order derivative of energy with respect to the number of electron, keeping the external perturbation fixed. So this chemical hardness is basically the variation of chemical potential again with respect to the number of electron, keeping the electron external potential fixed. Polarizability is also a second order derivative with respect to the electric field in different reactions. And electrophilicity, which is basically, if you consider, is uh, uh, this is some sorts of power, chemical power, is v square by r. If you consider the in the electronic circuit, we used the power as v square by r. Here it is also the same source, is mu square by twice eta. So mu is basically the potential, and eta is basically the resistance. So it is basically the chemical hardness, how hard the molecules, how it is difficult to perturb the system. and can be all these informations are included in this electrophilicity. One particular example we will see starting from the atomic system. So let's take a simple example: spherical confinement of atoms. So here we are considering atoms that are confined in a spherical box. Okay, that means if you just compress the atom by pressure or by some external things, then the confinement, due to the confinement, how the atomic orbital, how the energy, how the other properties, ionization potentials, or total energy, or V by T ratio, how does it change? That we will discuss here. And from now onwards, whatever we will discuss is basically the work done in our lab. So this model, this confinement model, is useful in many branches of physics, chemistry, and biology, and is useful for simulating the external conditions on the closed atoms. And this model is used to study the pressure on energy levels, polarizability of atoms and molecules, semiconductors, quantum dots, matter under high pressure, and impurities and defects. And physical properties of confined molecules depends on this confinement volume. We will see here. What is our methodology here? Initially, we have taken the wave function for the uh, unconfined system, and then if we do psi star psi, it will gives you electron density. And once you get the electron density of the system, this universal functional of the density functional theory, you can construct using this density, and then the total energy can be calculated using this. Okay, so nothing new, but the new here is that this how to confinement, how this confinement can be implemented in this model. So initially our wave function is basically terminated at the infinity. Now I want to terminate at the boundary of the box. So I used a Dirichlet boundary conditions to get the electron density 0 at the boundary. Okay, so ACF wave function, whatever I have, I multiplied it by a step function and then renormalized it. So I will get a renormalized wave function, and then iteratively I solve these equations. I solve these uh, uh, these equations. Okay, this is the simple methodology I used, and then what the result I get? The result is, let's say here, the softness is basically inverse of the hardness. So you see here, this is helium atom, and then this is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. Okay, so these are the helium is here, and then lithium is here. This is lithium, this is beryllium, then boron, carbon, nitrogen. That means you see helium is not that much soft compared to lithium. That means lithium is basically very reactive. Then beryllium, then high value of high softness value means more reactive. So systems are more reactive from lithium, beryllium, boron, and helium is here. Helium is very stable system. Neon, you see, is also very stable system. So because of the closed outer orbital, others are basically in the same as depicted in the periodic table. These are the ionic system: carbon plus, carbon 2 plus, carbon 3 plus, carbon 4 plus. Carbon 4 plus when means it is basically a helium with, it is basically a helium, no valence electrons. So that's why it's very difficult, very hard. However, C plus, you have only one electron left. So it is very soft. It will react very fast. Now, how does this confinement changes? Up to this much, you are basically not seeing any change. However, if you are basically decreasing the cell volume, means more confinement, then the systems are less reactive here also. Okay, and the polarizability plot also sees that the polarizability is also very less. That means that it is difficult to diffuse, to make changes of the electron density because it is less polarizable. When the confined, you are basically compressing the system, it's difficult to change its position, the electron cloud's position, and that is purely mimicked by this graph. So some other uh, results are also given here. This is the electronegativity plot. Electronegativity is basically increasing. This is the hardness. This is the electrophilicity plot. So how does this changes? You can get information of that. This is the total energy of the system. This is the kinetic energy. This is the total energy, and this is the potential energy of the system. Okay, so for all these molecules, so the changes of total energy or potential energy or kinetic energy is basically changes are occurring when the confinement are basically very less. That means the wave functions are basically basically compressing. At that time, you are getting this effect. Okay. So the conclusion of this particular work is that the softness, polarizability, electronegativity, and electrophilicity all are basically changing upon confinement, and systems gets harder, less polarizable, and less electronegative, softer and more polarizable upon confinement. And the softness you see here, the softness varies. This is softness and this is polarizability. Polarizability, one third of this polarizability is very good correlations we get between these two, softness and the polarizability or hardness, you can say also. So they are basically very well correlated, and uh, experimental observations for some small metal clusters are given in support of this theory particular. Okay. Now, this is the global property we have discussed. Now we'll discuss about the local property. This particular property we have proposed during my PhD time. So it is Felicity that tells you for a particular atom or for a particular molecule, which site is preferable for nucleophilic attack, for electrophilic attack, or for radical attack. So this omega is basically the electrophilicity of the system, and this F is basically the Foucault function. It is Foucault. Then this Foucault function is basically the change of electron density with respect to the number of electron if you change, keeping the external potential fixed. So plus, minus, and 0. So when it is F plus, you will get nucleophilic attack, and electrophilic attack is minus. So we propose that this omega K is the kth atomic site, which molecule, which particular atom, and alpha represents this. Plus means it is nucleophilic attack, minus means it is electrophilic attack, and radical attack it is 0. Okay. So this concept, if you want interested, you will get reference of this. Using this concept, we have tried to characterize these some of these aliphatic amines and which are the particular site for electrophilic attack and for nucleophilic attack. Okay, this is ammonia, then methylamine, and so on and so forth. Okay, these are the structures of these amines. Now, we have done calculations for gas phase and solution phase. Okay, so chemistry, gas phase is less interested. People are interested in solution phase. So we have done the solution phase calculations also. Here, there are two types of things in solution. One is explicit model and another one is implicit model. Okay, that means if you want to really mimic the experiment, then real molecule the solvent molecule you have to insert in your model. Otherwise, if you just try to get some results in a very less time, then you can use the dielectric medium of this solvent and then put the solve the solid the DFT calculations in that with that particular dielectric constant, and that will give you a very reliable results also. So solvent can be done in this way, and we have calculated the dipole moment and electrophilicity for all these systems. These are the values. So this is the electrophilic attack. You see, this is atom number 1, this is atom number 2, this is carbon atom, this is nitrogen atom. So electrophilic attack is possible here, and because this WK plus WK minus is maximum at this 2 is atom number here, and sorry, electrophilic attack is this is basically nucleophilic attack. This sign is not very clear, but it is basically WK plus in this side and WK minus in this side. So nucleophilic attack is on electrophilic attack is on the first atomic site. For both of these, first atomic site is nitrogen electrophilic attack, and this is basically the nucleophilic attack is possible on this side. This is according to your quantum chemical calculations. What we observe is that total energy dipole moment are higher in solvent medium than that of the gas phase, and the trend is reversed for global electrophilicity. Nucleophilic. Yes, please. This nucleophilicity index changes as one moves from gas phase to solvent phase, and electrophilicity index remains more or less same. WK plus value reflect the expected trend of the nucleophilic atom. Okay. Another analysis for benzidine. Benzidine molecule, we have considered how it reacts in solvent, and this potential barrier we want to find. If you rotate this system, this dihedral angle will change, and this is the rotational angle with respect to 0 to 360. Okay, rotations. And during these rotations, among this benzene rotates with respect to this benzene like this. Okay, so how flexible this molecule is when interact with the other molecule. If this barrier is very low, then it is very easy to rotate, and it can give so many conformers to interact with the others. But if it is a very rigid bond, then out of these several, only one possibility is there to interact with the other molecules. So that is why we are interested to see how flexible this bond is, so that how many conformers are possible, because benzidine is basically a toxin molecule, and we tried to characterize it. And with respect to the torsional angle, different reactivity parameters like chemical hardness, chemical potential, polarizability, electronegativity, how does it changes, we have seen. Okay, so this polarizability is minimum at this angle, where also you see the chemical hardness is maximum and energy is relative energy is maximum. That means in this particular position the system is very stable when the angle between these two is basically roughly 90 degrees. Okay, so how when it is changing also at each atomic site, how what are the local properties changes we have also shown here, and which particular site C1 and C5. This is basically your C1, and C5 is this one. These are basically symmetric site. These two sides are more prone for a nucleophilic attack, whereas this nitrogen is basically prone towards electrophilic attack throughout the change of this angle. Okay. How does this charge transfer takes place from system 1 to system from one system to another system? So using chemical hardness and chemical potential, you can calculate this. We have done this for several DNA base pairs: adenine, thymine, guanine, cytosine, uracils, and with this. So during this during these torsional changes, we have seen that the highest changes is occur in uracil and the lowest is in basically for the guanine. So relatively low barrier has provided greater flexibility and charge transfer between the benzidine and nucleic acid base pairs with the HH receptors has clearly revealed that the electron donating nature of the benzidine will come this again here. Using charge transfer between toxins and the biosystems, we proposed another quantity parameters, chemical reactivity parameters, which is basically the joint hardness. So how much charge is flowing from system P to Q is basically IP, ionization potential of the pH system, electron affinity of the QH system divided by 2. So it is basically this. So we have a reference. If anybody interested can see this. Using the using this, we have used these benzidine 3,3 prime dimethoxy benzidine and some other chlorobenzenes here, and what are the electron donating nature and electron accepting nature of these molecules characterized using three different approach. One is sign of delta n, which we have already shown. The joint hardness, which we have seen here. Okay, and another one is the electronegativity. Electronegativity principle you already know. Okay, so is from the lower electronegativity to higher electronegativity, electron will flow. That means electronegativity is nothing but the negative of chemical potential. So higher chemical potential to lower chemical potential, electron will follow. So this is basically Sanderson's electronegativity equalization principles. Using these two, we will now characterize. So delta n, if delta n is negative, charge is transferred from P to Q, and if delta n is positive, charge is transferred from Q to P. Okay, so depending upon the sign of P and Q, depending upon the sign of eta PQ, if delta n is positive, then it is from P to Q. If it is negative, then it is from P to Q, and if it is positive, then it is reverse reactions. Okay, so using this is my molecule. One set of molecule, another set. So each of these benzidine is acting with this dimethoxy 3,3 prime dimethoxy benzidine with this, and 3,3 prime dichloromethine dichlorobenzidine with all these molecules we have done, and these are the global properties we have calculated, and these are the charges. So here benzidine molecule is one fixed, with the other one DNA base is adenine, thymine, cytosine, uracil, ATH. What we have seen is that eta PQ is this one, eta QP is this, and delta N is negative. Okay, here you see all are basically negative. So our benzidine 3,3 prime dimethoxy benzidine, chlorobenzidine, and up to this one. Okay, but here you see when we are considering 2 prime 5 prime tri tetrachloro biphenyl, then here it is basically positive signs we are getting. Most of them are positive, except few are basically uracils when this is negative. That means using these three different approach, this benzidine, 3,3 prime dimethoxybenzidine and 3,3 prime dichlorobenzidine act as a donor, whereas 2,2 prime 5,5 prime tetrachloro by uh, biphenyl and dibenzofuran act as an electron acceptor, and guanine is basically the best donor, and uracil act as a best acceptor. So using these quantum chemical calculations, you can get amount of charge transfer between the two systems in different approaches, how much, which is donor, which is acceptor. Okay, so now most probably we have to stop. I want to thank first the resource, this computer cluster, and we have used basically Gaussian softwares for this particular works and some handmade codes, program codes for the first one. I would like to thank my PhD students who help us to make all these PPTs. Is Devolina. Devolina is now PhD and received his PhD. Harkishan, Nirmal, Sadhana, and Barsa, and past PhD students are Bedamani Singh, Pegu, Barnali, Rajkumar, and Jyotirmay Dev. And my collaborators, most of the works we have done with collaboration with Professor Potin Chattaraj from IIT Kharagpur and Paul Ayers, Bankmaster University, Canada. I also like to thank Nicolas Siriani, Bombanando Chakraborty, Sandesh Sharma, and Hatef Sadeghi for collaborative work. This part we will see in the next day, and funding agency DST, SARB, DVT, and BRMS. Thank you. Now, I hope I should stop, and any questions?